Okay, lecture 4, we'll talk about the water, very important component of the biological solutions in the biotech industry. And then we'll talk about data handling methods. Okay, first of all, water. So, we talked about different biological solutions that are important to maintain the integrity of the biological molecule, which are used as the API in the industry, right? So if you make those biological molecules, biological solutions, the main component of those biological solutions is water, because most of the solutions are water-based, right? So then the question is, what kind of water would you be able to use to make biological solutions? Of course, we're not going to use tap water because that's not clean enough, right? Then what else should we use? That should be very pure water that is validated and tested, right? So if you want to make like 1 kilogram of the recombinant protein, like API, through your upstream downstream process, it turns out you need about 30,000 liter volume of water, because the cell growth medium is water based, and then all those buffers that are used in downstream process as well as formulation, that's all water based. So there will be a lot of water used. Okay, so what are the main requirements for water quality? So like I said, it should be a very clean water type. Tap water is not enough because it's got a lot of contaminants. So what are the main contaminants can be found from water, like city water or whatever? And there will be organic molecules, inorganic molecules. There may be some fertilizers and different kinds, and there may be some living cells, so like bacterial cells that comes from sewer. So there are a whole bunch of contaminants that can be found. So take a look at your textbook, page 525, table 28.1. It'll list you what contaminants you can find from your water. Okay, so you will have to use pure water. Okay, and the definition of pure water is kind of a relative term, right? What do you mean by pure water? So there are different organizations that define different types of water. If you already did the lab, U.S. Pharmacopoeia defines the pure water as water for injection, UFI standard, but there are different organizations using different water quality. ASTM, ASC, CAP, NCCLs are different organizations with different standards. Take a look at your textbook to understand different water standards. Water quality and purification methods are different kind. Again, take a look at your textbook. So one of those standard systems lists water as different types, type 1, 2, and 3. So type 1 is the highest quality water. It'll be used for cell culture, tissue culture, HPLC, and buffer prep and things like that. So that'll be probably UFI equivalent water that you can use in the biotech industry. And type 2 water is less pure compared to type 1. It can be used for microbiology work and lab works of a different kind, maybe chemistry and biology kind of assays and experiments. That type 2 may be okay. And type 3 will be the lowest standard, and it may be used for maybe glassware rinse. Not the final rinse. Final rinse should be with the type 1 water, but when you wash it with detergent and things, type 3 water may be fine. It may be like deionized water kind. Okay, so like I said, according to U.S. Pharmacopoeia, the biotech industry, if they are making pharmaceuticals, injectable pharmaceuticals, they have to use water for injection quality. Okay, so what do you mean by that? We'll talk about that. So if you want to purify your water to remove those contaminants, what purification methods can you use? Okay, so you have to start out with the water that you can get. Normally the starting water would be considered as a feed water. Normally you use maybe city water as your feed water, right? And the city water will be treated with different methods. Number one method will be like distillation. Distillation means what? You boil water, then it evaporates, so liquid water becomes vapor, and then vapor will be condensed in a cold trap, so you have water recollected there. But since the contaminants in water, they have different boiling points, so you can collect water without getting those contaminants coming through at the same place. So that's how you can purify your water. Number one is distillation method. Number two method you can use is deionization method. When I say deionization, what does that mean? You can remove ions by running your water through charged ion bath. Right? You may have something like that at your home if your water is very hard, because you have charged ion bed. If you run your water through, opposite charge molecules will stick to the charged ion bed, and by doing so you can remove the charged particles. So that's deionization. So if you run your water through deionization, you call the water as deionized water. So that's one way of purifying your water. And another way of purifying your water is you can use a charcoal filter. So charcoal is what? It's a carbon compound. Carbons can bind well with the organic compound, which has a lot of carbon in it. So carbon has 4 electron empty holes in the valence shell, so it can stick with a bunch of other molecules that are carbon based. So charcoal filter, we call it carbon absorption. If you run your water through carbon absorption filter, you can remove a bunch of organic compounds doing so. So carbon filtration. And another way of filtering your water would be using different filters with different pore size. We call that filtration method. You can separate your water from contaminants. If you run your water through small filters with small holes, those contaminants will be trapped on the filter, and water will be purified by doing so. So it depends on what filters you're using. You could use something like nano filter that have very small pores, like nanometer size. Ultra filter, little larger pores. Micro filter in micron size pores, something like that. The reverse osmosis use maybe even smaller pore size filters. So that may be something like nano ultra filters. So if you run your water through reverse osmosis filtration, you can remove most of things like what? Viruses, endotoxins, bacterial cells, all those things. So filtration is a very efficient way of purifying your water. So when you use a filtration method, so filters come in these kind of cassettes. So to increase the surface volume, your filter may be folded this way, and your water will run through the filter by running the water through here, pressurized water, and going out. So that's how it's work. There are different filter types. Something called depth filter. Depth filter doesn't have really small pores. Instead, they have like these fiberish materials there. So these fiber materials can remove large chunky material. So depth filters are used as a pre-filter before your serious filtration. The microfilters, like I said, they have a pore size about 0.2 micron. 0.2 micron is small enough. It can remove all the living cells, including eukaryotic cells, fungi, plant, and bacterial cells, because they are all larger than 0.2 micron. So it's an efficient filtration method that can remove all living cells. Okay, and the ultrafiltration they have even smaller filter pore sizes. So ultrafilters are efficient to remove small things like maybe viruses. Okay. And then you have reverse osmosis. The name reverse osmosis is unique because reverse osmosis means you are running the water opposite to osmosis direction. So osmosis is what? It's a movement of water based on its concentration. That's what osmosis is. So water molecules will always move from higher concentration side to lower concentration side. That's like water diffusion. That's what osmosis is. But in this case, you are pressurizing water. So you're forcing water, so water can go through this filter that has very small pore. So on this side, there may be lower concentration water, and that may have higher concentration water because more water will go through this side and contaminants will be trapped there. So since the direction of water movement is opposite to osmosis, it's called reverse osmosis. It's a way of describing the directional move of the water molecule. But the important thing here is these filters have very small pores, like nanopores. So it is efficient to remove all the contaminants like viruses, endotoxins, and everything. Very efficient filtration method. And then on top of that, you can use strong UV light to oxidize any living cells that may be still present in your water. So in this picture, there's a UV light that shines that shows strong UV radiation, and the water molecule can run through there. When that happens, the strong UV radiation will kill, denature any kind of living cells or compounds that may be there. So it's a way of removing contaminants. Okay. So there are different methods that you can use to purify water. So then how do you generate UFI water? Normally you combine maybe several of those methods together. So tap water, it may be going through the deionization system first, and then it may be distilled, and they may go through micron filter, and then it may go through charcoal filter, it may go through nano field filter. So maybe combining 4 or 5 different steps, then you can develop UFI quality water. That's normally how you do it. If you go to a company like Catalan or Baxter, that's how they generate their own UFI water quality. Okay, so if you have a good water purification system, of course somebody has to maintain that, and the purification system should be validated to make sure that if it is really removing those contaminants or not. So how do you do that? By doing these tests and assays on your water. Okay, so UFI water, so QC technician will go out there and take UFI water sample, and they will measure these kind of things. Number one, they will measure the resistivity or conductivity of the water. So conductivity is correlated with the amount of charged ion still present in your water. If there are still charged ion present, conductivity will go up higher, right? But that's opposite to resistivity, because if you don't have any conducting material in your water, the resistance will go up. So resistivity, conductivity, you can use one of those to measure the amount of charged ion still present in your water. Okay, and then bacterial count, living bacterial cells, how many of them are found there. So you'll take water sample and plate it on a petri dish medium and see how many colonies you can find. CFU stands for colony forming units. That equals one single cell. So you should not have a lot of those cells, right? And then pyrogen, probably you did the lab already, or you will do it if you haven't done it. So pyrogens are endotoxins. Those are broken cell wall debris from gram-negative bacterial cells. They are made up with lipopolysaccharide layers. So they are very toxic substances that can induce the sepsis in human patients if endotoxins are injected to human body. Since you'll be making injectable drugs, parenteral drugs, your drug should not be containing any of these pyrogens or endotoxins. So you need to measure how much of pyrogens are still found from your water, pure water. Okay, so for that, so again, this is picture showing you LPS layer of the endotoxin. If they are injected to the human cells, they will activate the immune cells, so they will create the septic condition, sepsis. So to measure the endotoxin content, you can use horseshoe crab's blood lysate. So we call that Limulus amebocyte lysate assay. Okay, so Limulus amebocyte is the horseshoe crab's blood cells, and their cells are lysed, and there are special protein that can bind with the endotoxin. Okay, so by doing the assay, you can see how much endotoxin is still present in your water or not. So that assay can be done based on gel clotting ability, or it can be done on the color change assay, because that lysate can be conjugated with some kind of color-based material like yellow color. Then you can measure the amount of endotoxin based on the color change using a spectrophotometry. So that's called kinetic QCl assay, or if you want to do a gel clot assay, like the assay you did in the lab, that is considered gel clot assay. Which one is more sensitive? Of course, it's this assay, kinetic color change based assay. Okay. And then you need to measure the organic carbon content as well, because the living cells are made up of a bunch of organic molecules. How much of still organic molecules are still there in your water, that matters, right? So your charcoal filter should have removed enough of those, so you can measure that through your assay. Of course, and pH also is a simple check you can do, because if you have a pure water, it's slightly acidic. It's about pH about 5.7 or 6. That could be a good indicator of measuring your water purity. Okay, so those are the QC assays that are routinely performed to check the water purity in your facility. Okay, and then cleaning glass and plastic labware. So CIP, SIP, those processes are routinely performed. CIP means what? Clean in place. If you are trying to clean these large vessels like bioreactor, that's like 2-story tall. How do you do that? You cannot go in there. You cannot assemble this. Instead, you shoot pressurized water in there and detergent, and you rinse it a lot. At the end of the rinse cycle, that's a clean in place, and you also add pressurized steam in there, SIP steam in place. By doing so, you can clean it and you can sterilize the vessel. So when you do that, of course, the quality water is very important. So UFI water will be used as well. Okay.